To stay airborne, a bird has to constantly fight gravity. Every bank, dive, and hovering maneuver demands a massive, continuous supply of biological energy. To maintain that output, avian physiology operates like a high-revving engine, running on a highly optimized intake system. It starts the moment food hits the digestive tract. Specialized brush border enzymes lining the intestines immediately tear into ingested carbohydrates, rapidly breaking them down into simple sugars. To get those sugars out of the gut and into the body, birds rely on SGLT1. This transport protein acts as a turnstile, forcefully pumping glucose across the intestinal wall directly into portal blood. This massive fuel influx doesn't wander. It is shunted immediately to the liver for primary processing. This hyper-efficient pipeline from beak to liver guarantees that the avian metabolic engine is never starved for raw materials. Mammalian systems are designed to keep blood sugar levels low, using an immediate insulin response to pull glucose out of the blood. Birds, however, take the exact opposite approach. This table tracks average circulating blood glucose across bird orders. The class Aves average at the bottom sits at 15.6 millimoles per liter. This is more than double a typical mammal's baseline. For a human, resting at that level causes severe organ damage. This bar graph shows what happens to nectar-feeding birds after a meal. Those pink and orange columns highlight hummingbird species experiencing post-feeding spikes that shoot past 40 millimoles per liter. A spike that high would put a human into a diabetic coma. The avian body maintains this saturated bloodstream as a functional baseline, utilizing a glucose concentration that would be lethal to most other vertebrates. To manage a sugar load that would overwhelm a mammal, the avian liver acts as a central traffic controller. It triages the incoming glucose through a simultaneous three-pronged metabolic pathway. The first pathway is glycogenesis. The liver immediately begins packing away the excess fuel, linking the free glucose molecules into dense, stable chains of glycogen for safe storage. At the exact same time, it runs glycolysis. It diverts a portion of that incoming sugar straight into the mitochondria, burning it directly to meet the bird's baseline energy needs. And while it's storing and burning fuel, the liver is also running gluconeogenesis. It takes leftover precursor molecules, like lactate, and synthesizes entirely new glucose, pushing it right back into the bloodstream. By constantly running storage, combustion, and recycling all at once, the liver prevents the sudden systemic toxicity of a sugar spike, while carefully keeping the baseline blood sugar intentionally, persistently high. The reason the liver can maintain this balancing act comes down to the pancreas. Compared to our biology, the avian pancreas is a completely inverted control room. Mammalian metabolism is insulin dominant. Our pancreas releases insulin to pull sugar out of the blood. The avian pancreas is A-cell dominant. It prioritizes the production of a different hormone, glucagon. Glucagon does the reverse of insulin. It floods the system and acts like a molecular crowbar on the liver, aggressively breaking down those stored glycogen chains and dumping the freed glucose right back into circulation. But having all that sugar in the blood only works if the body's tissues don't immediately absorb it. Avian skeletal muscle is highly resistant to insulin. Evolution completely stripped out the GLUT4 transporter, the specific cellular doorway mammals use to absorb blood sugar into muscle. Without it, the circulating glucose molecules bounce right off the muscle cells. This insulin resistance serves as a key evolutionary filter, preventing the bird's peripheral tissues from prematurely draining the primary fuel lines. By combining a glucagon-pumping pancreas with insulin-resistant muscles, birds ensure their bloodstream is saturated with high-octane fuel at all times. You see the payoff of this system the second a bird takes off. An instant, explosive launch demands a massive amount of immediate cellular energy. There is no time to wait for the liver to deliver fuel. For these frantic, short bursts, skeletal muscles shatter local glycogen stores hidden inside the tissue, converting them instantly into rapid pulses of ATP. But local glycogen burns out quickly. For a 3,000-mile, multi-day endurance migration, burning exclusively glucose would exhaust the bird mid-flight. So before migration begins, birds gorge themselves, converting calories into dense lipid particles and packing fat stores throughout their bodies. Once they hit cruising altitude, they flip a metabolic switch. The muscles transition into beta oxidation. They completely ignore the high sugar blood flowing past them, absorbing and burning fat droplets instead. Shifting the physical workload over to fat reserves protects the steady stream of high-concentration glucose. It leaves all that circulating blood sugar exclusively reserved to feed the one organ that absolutely requires it, the brain. By evolving within this toxic metabolic window, birds possess a fuel system stable enough for 1,000-mile flights and explosive enough for high-speed evasion.